Yeah, definitely. And thanks very much for the introduction. So I think, what I wanted to more or less talk about today was how we see the future of AutoML, which we really are going to call an AutoML 2.0 approach. We're going to call it declarative machine learning. And so I'm going to walk through at least why I believe AutoML so far hasn't actually worked that successfully in industry and practice. I'll motivate that with actually what we see in terms of customer conversations and what we've seen directly from the community. And then a slightly different approach that I think accomplishes the same goals of AutoML, but taking a different approach than what was traditionally done by a lot of these first stab kind of providers. So as a really brief background on myself, my experience working in machine learning, as was mentioned in the introduction, I was a product manager across a number of different teams at Google responsible for productionizing AI. I was a PM with Google Brain that was really oriented on making models in production with Google Research. PM for what at the time was called Google Cloud AI Platform, now Vertex AI, which is GCP's machine learning platform. And I was also the first PM at Kaggle, which at the time that I joined was under 1 million users, but still fascinating to see that many users that had experience with machine learning. And today is actually north of 10 million users overall. And so it provides a really nice test bed to understand what types of technologies are working and not working overall. So some of what I share here will really be directly from my experience kind of in that organization as well. The key problem that I think, has always motivated me overall is that the benefits accruing from AI still tend to be quite polarized. We've seen a lot more companies now start to prototype overall in terms of how to be able to use machine learning to be able to solve one of the types of use cases that they might be interested in. But overall, the companies that are generating strong ROI are still the ones that you see kind of here, the Ubers, Facebooks, Apples, Googles, and others of the world. They're seeing machine learning drive a large amount of user engagement, retention, and growth. But 90% of the rest of the companies that we see are in an experimentation phase. They're seeing promise from AI, but not necessarily seeing the strong ROI directly from it. And I think that this idea that machine learning needs to be democratized has been talked about for a really long time. So the very first tweet that I could see that was around the idea of democratizing machine learning was all the way from 2012. And here we are more than a decade later, and we're still, I think, looking for that way that we can actually expand access towards ML to a much broader audience. And I think what we've seen over the last decade is that there's a class of products that have looked to deliver on the promise of being able to expand access to ML. And each year, it feels like there's actually more and more products that are being introduced in order to be able to hit that same vision because the pain is so strong. But more or less, they're really all taking the same approach. I'll go ahead and upload data towards my model. It'll go churn through a bunch of different smart parameter searches and model architectures and then spit out a model. I just don't think that we're actually seeing that approach really work and resonate in the industry. And one of the main reasons I say that is because I actually worked on one of these approaches in the past too. So when I was on Google and on Vertex AI, I actually worked on a project to be able to bring Google's AutoML to the Kaggle community, which at the time, numbered over 3.5 million data scientists and citizen data scientists that were really on the platform. And so I worked on this effort to integrate Google's AutoML a lot more closely into what we'd see day to day in Kaggle, whether that was folks that were sharing code directly for the purpose of education, or even just directly in our machine learning competitions overall. It was the perfect, in my mind, moment to try and bring the approach of AutoML to a more mainstream audience. And we actually got started with a lot of fanfare and buzz right out of the bat. Pretty immediately, there were plenty of reasons to be excited. We got picked up in the press for hosting a one-day competition called Kaggle Days with AutoML and data scientists in the same room. It was a really cool competition where we brought about 100 different Kagglers to compete against Google AutoML on a given data set. And where we saw AutoML excel was that it really kind of gave people superpowers. It allowed people to be able to build and try models that they never would have felt comfortable being able to do, a priori. And the second was it provided a structure that they knew was best in class. It really gave them kind of guardrails in terms of what were the things that would and wouldn't be okay for them to be able to experiment with directly inside their system. And they knew that the models that they were training with high likelihood would actually train, not fail on some out of memory error. And so with all that hype that came out of this initial experiment of seeing Google AutoML get embedded inside, a Kaggle competition, we were excited to see how it performed organically in the community when we released it for anyone to be able to try. And the AutoML usage looked roughly like this. At first, there was a lot of popularity and uptake. And we were, to be fair, pushing it quite aggressively because we thought we saw a promise for where this could actually really change data science workloads. But the churn was extremely high, and we didn't really see it take off. So as we try to understand why Google's AutoML and countless other AutoML products haven't really taken off in terms of organic adoption from the users that are actually trying to build and operationalize machine learning models, I would think it's important to be able to try and use like this type of testing bed to understand what's the gap between the promise of making it massively easier to be able to build models and the reality of a graph like this, which just indicates a lot of initial uptake and then a lot of churn very shortly afterwards. So the first thing I think we can do is try and look at, what do we actually hear directly from users? And so what do we see actually in the community? And inside of Kaggle, what we got hints of was this dead end problem that was a showstopper from people being able to actually use the model. Machine learning, as most folks here probably know, tends to be a last mile problem. And so you have like a great model setup that gets you an 80% solution, and then you spend your time iterating on being able to understand what actually works the best next. And instead, what we saw in Kaggle was AutoML helped users be able to get started really quickly, but it was a no-go for them to be able to use something that they couldn't iterate on. Oftentimes, what AutoML provided out of the box was a really good start, but not good enough to actually be able to use directly in either their competitions or in the case of organizations in production. That really mirrored what we heard from customers as well. And I think that this is just in some way, my view of the sad reality of talking to customers and being thought of as an AutoML platform is that people more or less immediately say, it's great to build a quick prototype, but they never use it for anything serious. This customer sort of thought it was like a toy. And I think that this really gets motivated with their experiences of using previous AutoML technologies as well. And the best summary, I believe, of the kind of industry application of kind of pain points of AutoML so far is an academic paper that some folks may have read that was published by UC Berkeley researchers, where a group of these researchers essentially did in-depth kind of user interviews with participants that had varying degrees of familiarity with AutoML. And they came to the conclusion that, while AutoML had merits that really made people strongly interested, people understood what the value proposition and promise of this technology could be, there were key blockers that stopped its eventual adoption inside of the organization. And those key blockers were really the following. The first was that it was a black box. So this is something that we've heard a lot of critiques on AutoML platforms, which I think have tried to address it by essentially saying it's not a black box, here's all of our explainability. But the piece about the black box that I think people really hated was the lack of agency. So the lack of fact that they could actually get in there with the model and be able to control it in the way that they might want, which is really the second key pillar, which is the dead end problem. More or less, at a certain point in every machine learning system, you hit a ceiling where you need to be able to go around it in order to fix either a bug that's come up in the system or be able to get that next round of performance. And one of the key issues with a lot of the AutoML providers today is that it's kind of like a single push button approach. You bring data in, it gives you a model, and you get the model out, but you don't really have an opportunity to iterate. And so what a lot of participants noted was, as soon as you need a mission critical project, you have to switch over to complete manual development. So that means throwing away what you had previously and building it out for yourself now. And then finally, a critique of some of the AutoML providers was that it's really kind of limited support for the things that go around model training. And so data pre-processing, post-processing requires other tools, and you have pretty limited support and you're locked into whatever is supported in the platform and the model today. My favorite takeaway from this particular paper, which I would say really resonated from our experience bringing machine learning or AutoML to Kaggle, was this one. Contrary to the idea of, the moniker of automated machine learning, practitioners do not use AutoML as push-button, one-shot solutions. Instead, they want to get into the trenches with AutoML during the model development process, instructing, advising, and safeguarding AutoML. Not treating themselves as consumers of an AutoML system, but really kind of co-pilots directly alongside them. And so this, to me, really informs, I think, where AutoML has had promise, and also where I think a lot of the V1 implementations have fallen short. And so to look at what success or great really looks like for these types of platforms, let's actually take a look at what did the 10% do. So we know that these 10% of companies were really effective at tackling machine learning projects day to day. And so what we can try and do instead is try and understand and learn from what their internal machine learning platforms look like. And so here, I want to actually call out that organizations like Meta have actually picked up on the fact that it's important, even internally, for them to be able to expand access to machine learning. This is a paper that details Meta's internal machine learning platform called Looper. And what they say is that to leverage AI more effectively, the system has to be able to accommodate software engineers without backgrounds in machine learning. So they share the same goal that a lot of traditional AutoML platforms had, but they're actually building this to be able to solve their own problems internally. And so I think we have a really nice opportunity to be able to learn for what worked for them. And it's not just Meta. This actually approach has been really adopted. The same approach has really been adopted by the internal machine learning platforms at many organizations to feed billions of queries and thousands of models in production across these organizations. And to me, the most fascinating thing about the success of this is that they've actually all taken roughly the same approach. They leverage a pattern that has been used many times to package machine learning behind a declarative interface, similar to what's helped make other complex systems like Kubernetes for infrastructure orchestration work really well. And then they just saw it organically take off from there. I happen to know this story intimately well because I can brag on behalf of my two co-founders who actually built two of these internal machine learning platforms at Apple and Uber specifically internally. Now, Pura's project on the far right-hand side called Ludwig is the only open source declarative machine learning interface. So I'll use that as an opportunity to show you a lot more about what I mean by declarative machine learning and why I think that it helps actually frame what the future of AutoML is really going to look like. So the key idea behind declarative machine learning is that it allows you to get started easily by allowing you to focus on the what rather than the how. So in Ludwig, as an example, which again is an open source project, meaning you can try this immediately, this 6 lines of configuration sets up your end-to-end machine learning pipeline to build a state-of-the-art text classification model. It'll automatically set up your pipelines all the way starting from data pre-processing, through model training, post-processing, and being ready for prediction. And so the really nice thing about this is that a user can get started as simply as just specifying what are the inputs and what are the outputs of this model that I care about. But the best thing really about the system is you can customize any part of your model pipeline as you want in a series of one-line declarative statements. And this really tackles the idea that you don't need to throw away your initial model in order to be able to customize it further. So as an example, now with traditional AutoML systems, customizing your models would mean throwing away that system and starting from scratch so you can write the low level of code yourself. And here's just an obligatory slide on the, showing you how complex that can get. First, you'll need to re-architect your data pre-processing pipelines that might involve complexity and wrangling, feature normalization, scaling, and others. And then you'll have to get into the internal guts of your model. So how do you actually do things like the actual forward passes and others for this model training? And then you'll have to actually get into the infrastructure of training, which might mean having to deal with CUDA, and many other kind of low-level drivers in order to be able to make this successful. And at this point, we haven't even talked about the iteration, the debugging, the serving, and much else. So this is what it looks like, for example, to be able to add like an LSTM to be able to do the NLP task that you might be interested in this particular case. Instead, any of this iteration and customization can just be expressed by a single 2-line configuration change. So if I wanted to use an LSTM to be able to encode my text features, all I do in Ludwig is say I want an encoder, and the cell type will be an LSTM. And that allows a user to be able to have as much flexibility to be able to specify anything from hyperparameters they want to be able to search over to model architectures that they're interested in being able to use just in a series of configuration-driven statements. What we like to say is the user figures out the what they're interested in, and the system will figure out the how, so they don't need to re-implement any pieces of this architecture themselves. So in our view, declarative machine learning, which is this idea of being able to just simply in one-line statements be able to specify parts of their machine learning pipeline, is the 2.0 for AutoML. And AutoML 1.0, which was this push button, let me bring my data and let me get a model out and not iterate further, was just the starting point overall. I think the reason that we see declarative machine learning have much more organic uptake is because ultimately teams want both simplicity and flexibility. They want to be able to both be able to have an easy way to be able to build their models, but a way to make sure that they can continue and aren't stuck when they actually need the models that they want. If I had to summarize these two approaches, using an analogy, one of my favorite ones is actually comparing it to how we might drink coffee. On the left-hand side, you have things like building your models with low-level APIs and frameworks. To me, it's like brewing your own coffee. You need to grind your own beans, have all the right equipment, be an expert in coffee beans, and it'll probably take you several hours. On the right-hand side, we have things like traditional AutoML, which is a little bit more like instant coffee. It works as a quick fix, but no one that I know actually really wants to drink instant coffee. I see declarative machine learning as a lot more like ordering coffee off the Starbucks app. So you can leave kind of all of the, you can leave your model or your coffee drink as a baseline, customize anything that you want, how many pumps of syrup you want, how many shots of espresso you're looking for, what kind of milk. You can choose and customize everything that you want and allow the system to be able to automate the rest. And so ultimately what we think is that declarative ML bridges both the benefits and the flexibility of the low-level APIs with the simplicity of automated machine learning. And so if we were to reflect on those prior takeaways that we saw, previously, in terms of what the shortcomings were for traditional AutoML systems from an interface standpoint in particular, to be able to actually make machine learning more accessible, I would say we see that instead of a black box, we really have more of a glass box. Instead of being able to just instead of having a model thrown at you, you're able to configure pipelines down to the level of code if you want to get there and have all the levels of abstraction to be able to work out on it at a higher level. Instead of the dead-end problem, this entire system is oriented to be a lot more human in the loop. It's extensible, it's iterative, it allows a user to be able to kind of actually come in at any given point and add those levels of customization that they think are required. And then finally, instead of limited support and lock-in, it's really end-to-end and it's open source. So you're able to go ahead and support everything from data pre-processing all the way through post-processing with training in the middle. And it supports an open source foundation in terms of the models that are actually supported and done. And because it's open source, you don't really have to take my word for this. You can go ahead and try out Ludwig directly today. It's been a reasonably popular project, over 9,700 stars. If you can help us break 10,000, we'd love that. And we see a number of different contributors that are able to actually be able to get alongside this and work with us in making sure that this becomes best in class. And one thing I want to do is indicate that it's more than actually just a really pretty interface. Ludwig has not only a really deep configuration language that allows you to customize and extend the modules that you might want. For example, allowing you to have expert level control and how exactly you want to be able to set up your trainer if you've gotten to that point, and advanced functionality that does things like hyperparameter optimization in a very intelligent way. You have all of this kind of controllable via like a simple configuration language, but it also sits on top of what I think is a really interesting compositional neural network architecture. And what this essentially is an architecture that we call encoder, combiner, decoder. It allows you to have many different types of input fields, text, images, tabular data, and be able to encode them with best-in-class models that you might be interested in. For example, for an image field, you could use ResNet or VIT, which is an image-based transformer. You could then combine that with a text field with which you might use something like a pre-trained but fine-tunable BERT model. And you can easily stitch together any parts of these models into a simple machine learning pipeline that works end-to-end, again, all the way from pre-processing, encoding, combining, and decoding. So with Ludwig, what you can do is work easily with any of these different types of data modalities, as well as model architectures, and compose them together without having to figure out the hard part yourself of how to be able to use kind of multiple different stitched machine learning models and transformers into one pipeline. So I think that's really the power of everything from an abstraction standpoint, and from making it easy to be able to have the task flexibility. And then when we speak with more, advanced organizations, they say that this is something that's great. They're able to get it running locally, but is it ready for prime time? Because prime time means SLAs from data connections upstream and a real model serving story. And that's really where 95% of the talk here has been about what's in the open source. And what I would just say, Predabase, the company we started 2.5 years ago, is really oriented on being the fastest way to go from data deployment, built around this core architecture of Ludwig. So we take this notion of being able to declaratively build models, and we build an entire platform around it, from data connections to a model repository experience to make it easy to be able to track, iterate, and refine models. And then finally, a way to be able to deploy those models for real-time inference. And so with that, I'll just go ahead and say, please feel free to try us. If you're interested in being able to try us just directly in a notebook, the easiest way to be able to get started is just to go to ludwig.ai, and you'll be able to see a number of different examples that support everything from LLM fine-tuning to supervised machine learning use cases like image classification, fraud prediction with GBMs, and everything else using the simple configuration-driven interface. And if you want something that actually has a little bit more of a managed experience, that will allow you to have the infrastructure without having to pay for the GPUs yourself, maybe, you can actually try us for free on Predabase as well. And when you start here, you'll have a number of different quick start examples. Anything from fine-tuning Llama 2 7 billion on a particular task that you might want to do. Again, you can do this for free on our platform today, to training a more supervised machine learning model is kind of all supported directly inside this. So I'd encourage you to give us a try and see if declarative machine learning helps actually bridge the gap that we often see from traditional AutoML or the 1.0 approach, as we call it previously. So that's a little bit of what we've been working on and building. Would be more than happy to answer any questions, and hope that you get a chance to try this for yourself and determine if it actually lives up to the promise and the hype.
Thank you. All right, any questions from the real or virtual audience? Yeah, go ahead.
Can you hear me?
Can you, oh, actually I think I should unmute. Okay, try again. Can you talk now?
Hi, yes, can you hear me?
Yes, I can hear you now.
Very interesting topic, thanks for the talk. My question is regarding the configuration which you showed. I could see we could configure like input features, output features, and what kind of models, and more like you can get into details. Is there also some kind of support to include some interpretability, like say some kind of explainers as a configuration? Is that also like possible?
Definitely. So explainability is something that you have access to. We provide some explainability models right out of the box. So everybody seems to support SHAP out of the box. We also support SHAP, but we also support other techniques like integrated gradients, for example. And you can see your feature level breakdowns here that you might be interested in. But you can also see token level breakdowns for text fields and others if you're interested in that explainability. So yeah, I think you nailed it when you said you have some configurability. Can I configure the way that my model is actually going to do explanations? And like the answer there is definitely. You can more or less configure any part of this pipeline. And so by default, we use integrated gradients. But if you wanted to use a different technique like SHAP or line, that's something that's supported as well.
Any other questions? So what do you think are the most exciting future directions for further improving Ludwig?
Yeah, it's a great question. To me, Ludwig has always been this deep learning first platform. And earlier this year, people got really interested in this class of deep learning models, which I think, specifically were around large language models. And so I think to me, the most exciting direction that Ludwig has already been headed in, but like to continue to really double down on, is being able to use our training interface for larger and larger open source language models, and being able to do very clever things in terms of how we can optimize the use of those open source language models. So in Ludwig today, you have things that you'd immediately expect. For example, if you want an instruction tune Llama 2 7 billion, maybe using like 4-bit quantization so you can run, I think quite literally inside of a Colab notebook. That's what you're interested in. We have this Colab notebook that you can check out. I think that all exists immediately, but what I'm really interested in is being able to bring more of the LLM training best practices that we see coming out of the labs today directly into Ludwig so people can consume it just off of a one-line configuration change. As one example of like one of those extensions that I'm quite excited about, it's the ability to do things like speculative decoding is something that allows like LLMs to be able to speed up inference. And essentially it works by fine-tuning the LLM on what its predicted output would be so that it's able to run inference faster using multiple decoding heads. And so I think that's like a type of functionality we can bake directly into Ludwig and make it so that people can have faster inference LLMs just with a single config change. A second thing that I'd be really interested in is being able to extend and expand on Ludwig's self-supervised learning capabilities. So the idea here could be not only instruction tune Llama 2 7 billion, but you can do the same process you take for pre-training a large language model and do it as well with any of these. So those are two directions that I think would be really interesting for Ludwig in the future.
Got it. Yeah, it sounds like they'd be very useful, nice features. Yeah, Marius?
Thank you very much. This was very insightful. I'm still struggling a bit with this idea of saying that you can be declarative, more saying, here's only my data and then do something with that, right? So more like fully automating everything, but on the other side, you can also say, here's my architecture and I'm much more fine granular, right? But how should the user decide on what kind of level of granularity they need?
Yeah. So to me, I think the most critical thing here is that machine learning, folks that are working on machine learning and data scientists are not created equal, neither are the tasks. And so the level of granularity you need just scales with the sophistication of the task and the user. And what most AutoML interfaces, in my opinion, have are they allow you to operate at like one of two levels of granularity. You either get the really coarse level, like where you just basically get a push button, or you get something much more advanced, but that's inaccessible to an entry user. So to me, the ideal experience is something that allows you to start easily and then be able to iteratively extend kind of what you do over time. And I would argue that this declarative and configuration interface does exactly that. And it's what we see from our users in the open source. Most users, when they build their first model, start off with something as simple as like a 6 or 8 line configuration, like the one that you see. Then they evaluate, see where that's actually doing well or not, and they start to add more and more lines of configuration as that time goes on. In terms of the level of granularity of support that's needed, I would say that's just that is really just the task dependent. For, I would say, the vast majority of our users, they get, the delta they need by choosing different models and encoders. So maybe using a pre-trained model and then fine-tuning it for some of their fields. But some of our users really get quite complex, down to the point where they're learning a lot more about the way that we would do hyperparameter optimization, using cyclical learning rates, changing our optimizers. And if a user wants to get that advanced, we do support that. And that's something that we think that, eventually it's just about having the depth of choice to be able to support what actually exactly a user wants. So that's the exact problem I want to solve for, which is how do you have an abstraction that's easy to get started with, but actually has the depth to be useful, beyond your first model.
All right, thanks. Any final questions? All right, let's thank the speaker again.